Okay, let's continue. So, hope everyone is full of energy after lunch and lots of lectures. So, today, following my, uh, by the way, I have no ambition of getting somewhere. Okay, so I will just tell you as much as I can with the time we have. So, interrupt. I'm happy to go on a tangent. So today, let's start. So yesterday I told you about I gave you some basic motivation, right? That hopefully makes you excited about this research program. If you're just trying to understand the beginning of the universe, I hope that that's good enough. So then we discussed the major novelty of quantum field theory in curved space, which is this vacuum ambiguity and particle production, spontaneous particle production. Then I gave you some basics of the classical geometry of de Sitter space, okay? And we discussed the isometries of de Sitter. So now we're gonna just quantize the free scalar field. In de Sitter. And you'll see that there's a novelty. So you remember Wigner taught us that a particle is related to representations of space-time symmetry group. And in Poincaré, in flat space, you have the Poincaré group, and then that's it, right? And then particles are massless or massive. There's no such thing as heavy or light. In de Sitter space, because there's a scale, there is a sense in which particles are light or heavy, because you're supposed to compare their mass with the intrinsic energy scale of de Sitter space, the Hubble scale. So we're going to see that even for scalar fields, the representation theory is peculiar. It's different. And we're going to, instead of me embarking you on some crazy discussion of a la Wigner, I'm just going to quantize the free scalar field and we'll see. So the action is the usual. So this is the action. And remember that the metric I wrote yesterday, so let me write it again. We're going to quantize in these flat slices. So because there is translation symmetry in this position space, we're going to go to momentum space. So this is 3 momentum, okay? There's no energy because there's no time translation symmetry. But by the way, well, I'll tell you in a second. So, well, the first step is to understand the classical equation of motion to quantize. So, for classical equation of motion. So first of all, you just Fourier transform. You think in terms of Fourier mode. So you go from phi depending on x and eta to some phi k that depends only on eta. So that's the usual trick. And then we'll see that each Fourier mode is a time-dependent harmonic oscillator, just like we discussed yesterday. And well, moreover, you see there's a root g and a g mu nu. So there are going to be some factors of eta that multiply the space-time derivatives. So let me just canonically normalize to make the action look a bit more familiar. So I'm just introducing some field redefinition. This is nothing deep, although it has a name. Or maybe let me mention the name because you might see in the literature, but it's nothing fancy. This is called Mukhanov-Sasaki variable. So if you plug this in the action, then the action becomes, I need my cheat sheet here. So it looks like this. The eta v squared minus the v squared minus, and then there will already be something peculiar going on from the canonical normalization. I don't know how it works in your country, but when I'm from Brazil, okay, so when you are in grade school, you learn that you should do parentheses, the innermost layer, then these square things, the outermost, and the outermost, it should be this. Does this ring a bell to anyone? Yeah. Ah, okay. I thought it was only in Brazil. Okay. No, because I remember when I got to the US, I started doing this for my PhD. People were like, "What the hell are you doing this?" So anyway, so now I have some schizophrenic take on this whole. So notice something interesting. First of all, there is definitely a difference if the mass is big. If the mass is very big, it's the usual mass term. This -2 doesn't matter. But if the mass is small enough, let's say smaller than 2 in Hubble units, then this looks tachyonic. But it's completely fine. So all massive representations with m squared positive are completely fine and unitary, but it looks peculiar, it looks tachyonic. So what happens is that the particle production in de Sitter space is tremendous. So it looks like there's a runaway, but the runaway competes with the expansion of the universe, and you get some finite density in the end. But the behavior of the correlation functions of the scalar field will depend on how heavy the mass is in Hubble units. Okay, so now if you go to momentum space, I'm just repeating. So the equation of motion for this Mukhanov-Sasaki variable, the classical equation of motion looks like this: k squared plus m squared minus yeah, it is I mean, if you change to the ADS radius, you see that it is the BF bound. It's just that the BF bound tells you that tachyons, they're not too tachyonic in ADS, are acceptable. And here it says that light enough fields in de Sitter space, they look tachyonic, but they're also acceptable. But if you go back to that original Lagrangian, you want m squared to be positive. Okay, so this is more like telling you BF stands for Brighton, Lohner, Friedman. There's something about admissible tachyon. So ADS acts as a box. So tachyonic instability tells you that negative mass squared tells you that things grow, but because ADS acts as a finite size box, the tachyon doesn't manage to grow too much to violate unitarity. So a small amount of tachyonic mass is acceptable in ADS. And here the physical interpretation is more like for masses that are light enough in Hubble units, you have very violent particle production. While for masses that are heavy enough, the particle production is more standard. You get just a handful of particles per unit sphere. You have the de Sitter space kind of. So there was a question in the question session about the infrared behavior of flat space. So when you have cosmological constant, the cosmological constant does something in the infrared, right? So in ADS, it acts as a box. So in fact, people say, well, if you want to regularize a theory of infrared divergences, it's an old paper of Kahl and Wilczek. You just put it in ADS. So it acts as a natural infrared regulator that doesn't break any symmetry, or keeps maximal symmetry. Definitely changes the symmetry, as now we now know when you're learning. And the Sitter space is more like, instead of putting the system in a box, is the ultimate separator. It makes things ultra local, so it pulls things apart, and then the perturbations, they just care about a Hubble-sized box. Okay, so that's the difference. So for masses that are small enough in Hubble units, inside each box you have a bunch of quanta. While for heavy masses, you're going to have just a handful of quanta per Hubble-sized box. Okay, now if you stare at, well, maybe it's not so obvious, but if you stare at this equation, you will see the other thing that why you get just a handful of quanta per Hubble box. So if you go to late times, if you recall from yesterday, it's eta going to 0. Then no matter if it's becoming very heavy, the field. Okay, the mass term is becoming very heavy. So the field is just redshift, just the physics of redshift. You've seen that giving the physical distance really goes like x over eta. So when you look at fixed wave number, it's unphysical because the physical wave number is changing with time, is being redshifted away. Okay, so in particular, there is a piece of jargon. This is jargon, okay, but it appears so much in the literature that you should learn. Horizon crossing. So the idea is that if you track a fixed co-moving wave number mode, K, the physical wavelength is changing with time. So at some point, the physical wavelength becomes equal to the de Sitter radius. And when that happens, that's when particle production is most extreme, because when the physical wavelength is much smaller than the Hubble radius, the mode doesn't care that it's in curved space. It's as if it's in flat space. When the physical wavelength is super big, then if you wish, the mode freezes. Freeze is not the right word. The particle production is dominated by the moment in which the physical wavelength becomes of order the de Sitter radius, and we call this horizon crossing. Okay, why is it horizon cross? Okay, so mathematically it's this equation. Okay? So for every k, there is a particular time, eta, in which most of the fun happens. Okay, so for very early times, it's just oscillating like a standard harmonic oscillator. Then as eta becomes order 1 over k, there's a burst of particle production, and then this particle number remains more or less conserved, and the further evolution is dictated by how heavy the particle is, just standard cosmological redshift. Okay. Why is it called horizon crossing? So if you look at the Sitter space in this flat slicing, so these are just Euclidean planes, the flat slices. So if I take a point here and I shoot backwards a light cone, then you will see that if I'm here lecturing for you and you in the audience are here, in 10 minutes from now you cross the horizon, we'll never hear anything I say again. Okay, so we lose causal contact with each other forever, and no matter how fast I go, I'll never be able to catch up with you. So you fell outside of my horizon. So there's a natural horizon. By the way, a small philosophical point. We know that the universe is undergoing accelerated expansion right now. We have a cosmological constant. That means that we'll never be able to see the whole universe. Even if you wait 1,000 billion years, the Penrose diagram of the universe does look. There's some earlier phase. I have no idea how big it is. Some earlier de Sitter phase, radiation domination, and so on. But the point is that let's say we're somewhere here. I mean, there's no time. This is all time in the universe. So if you wait infinite time, you're only going to be able to see so much. So I don't know if that makes you depressed, but so there is some amount of information that you'll never learn, unfortunately. That's in flat space. That's not true. They call this People that studied this landscape called it the census taker hat. Like, so, wow, the Penrose diagram of flat space looks like this, right? So even if there's some cosmological evolution, if you wait long enough, you collect all the information in the universe, okay? But that's not true in our universe. Anyway, going back to our standard discussion. If you look at the formula, then you will see that the behavior of Vk changes considerably for eta much less than 1 over k, or order 1 over k, or bigger than 1 over k. For eta very small, let me, actually, you can, this is a standard Bessel equation, okay? But let me write to you the full answer. This is just so you know that there is a closed form answer. There's no, I don't expect you to read any physics out of this formula, but let me just write it down. So this is the classical answer that we're going to choose to quantize. Remember, there was a choice of what classical answer. So if you do everything to the book, no. This is called a Hankel function of the first kind. And the Hankel function of the first kind is defined to be the Bessel function, the standard Bessel function, plus I times the modified Bessel function. Of course, you see nothing from this form. Well, if you do, come talk to me after the lecture. But if you, the point is that Vk, if you look at very early times, you can neglect the second term. It's just standard harmonic oscillator. And this is the choice for which Vk goes like e to the minus ik eta. Okay? Now there was a question yesterday by someone asking, well, what about the vacuum ambiguity? I'll take your question in a second. What about the vacuum ambiguity? Why don't you take an admixture of positive and negative frequency? To which I'll say it's a completely fair proposal. So here I'll tell the words that people usually say to make peace with this choice. The words go something like this. Well, if I go to very early times, if I keep track of a fixed comoving scale, if I go backwards in time, the mode is getting more and more blue shifted, so it looks more and more like you're in flat space. So you should quantize like you quantize a harmonic oscillator in flat space. Now, of course, the catch is that there's no Hamiltonian to minimize. So you can try to define some Hamiltonian here. Maybe try to make some time translation be an isometry. Find that there is no generator that is manifestly positive and is conserved in de Sitter space. That's why supersymmetry doesn't like de Sitter space, right? Because if you square one of these supersymmetry generators, should give you the Hamiltonian. Therefore, the Hamiltonian is manifestly positive. And there is no manifestly positive symmetry generator in de Sitter. So there's no energy to minimize. Strictly speaking, you have the freedom to decide to quantize with an admixture of positive and negative frequency modes. These things exist. They're called alpha vacua. Okay. So, but I do not recommend that you go in this direction. But I guess full disclaimer, it would be choosing quantization Vk alpha to be e to the minus ik eta plus alpha plus beta e to the plus ik eta. Okay, there's some standard parametrization with Bogoliubov coefficients. They're completely fine at the free level, but if you try to make sense of interacting field theories in this vacua, then things become funny very quickly. So I'll make some comment about this later in the course. So I'm going to make this choice. And this choice comes with many names. I'll tell you in a second. But maybe let me take the question. Yeah. Ah, no, because this k is the absolute value. I forgot to say k is the absolute value of the 3 vector. Yeah, so it doesn't matter. But if it's yeah, so it's e to the I k dot x phi k classical or eta ak. So that's what I'm plus Hermitian conjugate. Yeah. So that's what I'm. So phi is integral. I guess the 3k. Yeah. So that's what I'm. Yeah. You need the Hermitian conjugate. Otherwise, it's not real. So it's just like we did in the previous lecture. Okay, it's just each Fourier mode is a time-dependent harmonic oscillator. Now the annoying thing is that, okay, as eta goes to minus infinity, you have the nice in region in which you can decide to quantize, and then as eta goes to 0, there's no out region. So there's no region in which things really the background is switched on forever. Oh, that's done. That's the distinction. You can try to regularize, but people don't like it. I'm happy to tell you why later. So this has many names. So let me tell you. So this is called Bunch-Davies vacuum. Maybe it's the most popular name. Then, as usual, someone behind the Iron Curtain had done it before. So it's Chernikov, Tangirov. Then also called the Hartle-Hawking vacuum, because they generalized this prescription to include gravity. And because it's essentially the unique choice of state to define correlation functions in Euclidean space. It's also called the Euclidean vacuum. So given that Euclid is the oldest of all of these people, maybe I call it the Euclidean vacuum through the rest of the lectures. Okay. So this is, there is the vacuum ambiguity, but we only know how to make sense of the theory for this choice of vacuum. So if you impose that it behaves as e to the minus ik eta as eta goes to minus infinity, then, and you fix normalization, you get this Hankel function of the first kind, okay? There is a second kind of Hankel function that would then give you positive e to the plus ik eta. And last piece of terminology that I erased on the board. So we will call this energy. So there's no energy, but if you think of every mode as, even though they have masses, if you think of every mode as being related to a massless particle, this would be the energy of the associated massless particle. So this is a very useful piece of notation. Remember, there's no time translation, no energy conservation. Nonetheless, it's very useful to think of the absolute values of the momenta as, and calling them energies. That will become more and more natural as the lectures go on. So if you study, I forgot to, nobody asked me. I forgot to define nu. Nu squared is 9/4. So actually the interesting behavior is not, it's funny, it's not at 2. The transitioning behavior happens at m over h order 3/2. Okay, not square root of 2. So let me say a couple of things about, so this is really a damped harmonic oscillator. Okay, the damping comes from the forcing, and the damping comes from the expansion of the universe. In fact, we even call this Hubble friction, because you're trying to move and the expansion of the universe slows you down. So you also hear this jargon, Hubble friction, coming from the fact that you're studying this harmonic oscillator in de Sitter space. So one way to think about it is if you plot here m over h, then if you look 0, then well, this is order 1. Okay, it's a 3/2 or whatever. Then you should think of this. So this range here redshift doesn't affect. I'll show you in a second this fluctuations. Or there's a cancellation between particle production and dilution. So we'll see that. Then here it's more or less the critical regime of the harmonic oscillator. And here you have overdamped oscillations. So this will behave more like matter. Okay, so for particles their mass bigger than Hubble, then the answer will ring a bell and it will look more like matter. So even though there is a region in which as eta goes to 0, there is really no out region. When the mass is much bigger than Hubble, you can write something nice that will give you some intuition of what's going on. So for m over h much bigger than 1, now I'm going to go back to phi k, okay? Phi k classical, not the Mukhanov-Sasaki, because it's gonna the exponent looks nicer in phi k classical. It will make more sense. Phi k classical as eta goes to 0 at late times looks like this. Remember, I imposed that the mode function should behave like plane wave or positive frequency at early times. So whatever happens at late times is what happens. So here's what happens. You're going to get eta to the 3/2 times eta to the minus im over h times some coefficient that depends on the mass plus eta to the im over h C2. Okay, this C1 and C2 depend on the mass. So what does this look like? Let's look at particle production. No? You get, let's remember that eta, so this is peculiar because at early times, you erase the mass information and it looks like a plane wave in conformal time. But conformal time is related to cosmic time like this. It's minus e to the minus ht over h, I think. Yeah, 1 over, yes. This is the usual way of writing. So if you change variables like this, then you get the usual minus dt squared plus e to the 2ht dx squared. And if you plug this here, what is this? It's e to the imt. Okay, e to the minus imt. C1 plus e to the imt C2. So what is this? The rest energy of the particle. The particle gets redshifted away. The motion of the particle freezes. It only has its own rest energy. But you have an admixture of positive and negative frequency, so you produce particles. So in each Hubble volume, the particles, they stay put, but you have some number of particles. So that's the picture. So at very early times, you get just in the in region, you get just a positive frequency thing, you're in the vacuum. And then at late times, if you look at each Hubble volume, now there are many Hubble volumes because the space-time inflated quite a bit. Each Hubble volume has a burst of particles that lay at rest inside of the volume, and it's controlled by this Bogolyubov coefficient, okay? You can even compute, you can play these games that we played yesterday and compute. This I'm just telling you the result. You compute, it doesn't depend on K, by the way, because of redshift. The number of particles from the point of view of the out vacuum, if you decided to quantize using e to the minus imt, is going to look like this. It's going to 1 over e to the minus m over TDS minus 1. So this is a Bose distribution, right? And the temperature is h over 2 pi. This is the de Sitter temperature. Actually, it was first described by Italians, by Chiara Nappi, people in Napoli, before Gibbons and Hawking. This is called the Gibbons-Hawking temperature. But, maybe, can you give me a little bit more information? What? Well, I said after here I said the following. If you look at, I'll comment about this in a second. If you look at this part here, and you go to cosmic time, you go to the variable t instead of eta, then these two terms look like plane waves, right? But first of all, there is no dependence on k anymore, so every wave number is frozen. And because you have an admixture, there's particle production, okay? And the amount of particle production is also mode independent. It follows a Bose distribution at a certain temperature. And this temperature is controlled by the Hubble scale. So for heavy particles, for mass greater than h, because their Compton wavelength is smaller than the de Sitter radius, the Sitter space looks like a box at a certain temperature, okay? This is called the Gibbons-Hawking temperature. But this interpretation is really clean for heavy particles. For light particles, well, it's not so clean, the interpretation, because they have very big Compton wavelength. The Compton wavelength is bigger than the de Sitter radius. So they behave a bit differently. By the way, anyone knows why these 3 halves here? If I compute the 2-point function, it goes like eta cubed, okay? So what does that remind you of? A scale factor is 1 over minus 1 over h eta. It goes like 1 over a cubed. Does that remind you of anything? How does matter dilute as the universe expands? Like 1 over the volume, right? 1 over a cubed. Just a matter dilution. This is redshift. So redshift, these redshifts like matter, and the envelope is related to particle production. Okay. So if you look at the 2-point function, if you look at the 2-point function, you get a burst of particle production, but then it decays. It decays like matter would. So if you look at the phi 2-point function, the function of time, it decays like matter would as 1 over 1 over a cubed, with some envelope and oscillations that are controlled by the mass. Okay, and the amount of particle production is also dictated by the mass. So this is what I can tell you about the generic case, just to get you some intuition. So there is a clear sense in which massive particles, so in fact they fall into three representations. So the massless particle, it's called the discrete representation of the de Sitter group. Then the light particles before the critical regime, they're called complementary series representations. They really have power law behavior. They decay is not oscillatory. So they're 2-point functions, they decay like a power law. It behaves more like a CFT correlation function. And then the standard massive particle that you know and love from flat space is more like to the right of the plot. And these are called principal series representations. So they have this usual dilution of matter plus some amount of particle production. Let me emphasize now two cases. There will be I'll emphasize two particular cases of the mass. One is m squared equals to 2h squared. This is called the well, I'm sure I will not be consistent, but in my notes, this is in blue. So let's see how that goes. So this is called the conformally coupled scalar. That's because for m squared equals 2h squared, you're really just describing a massless field in flat space. There's a conformal transformation that turns this action. You can interpret the action in two different ways. It's a massless field in flat space, or you do a field redefinition. It's a field of mass equal to 2h squared in de Sitter space, okay? And it's clear to see how the phi k classical is in that case, okay, if you canonically normalize, there's an h over root 2k. But look, so if you absorb this eta into some redefinition of phi, you just get the massless scalar in flat space. Okay. So it looks like a massless plane wave, the classical solution. And more, okay, but in de Sitter space, it dilutes. Okay, so it goes to 0 as eta goes to 0. It goes to 0 like eta to the 1. Okay. So from the point of view of fall off at late times, it has a scaling dimension delta equals 1. I'll comment on what this delta means in a second. But now the interesting case is massless, m squared equals 0. That's the case in which at the boundary of unitarity, my color code tells me it's red. And in the ideal world, if I was a robot, I would use var phi and phi but I'm sure I'm going to mess it up. So var phi in LaTeX produces this, and phi produces this. So just so you remember, this is conformally coupled, and this is massless. And this is the mode function, and there is a essential difference. So for these two cases, interestingly enough, the Hankel function becomes just a simple exponential times some potential, times some polynomial. Now notice the following: as eta goes to 0, it goes to a constant, h over. And now we're cooking, okay? So this is remarkable. It's the case in which the universe is trying to redshift away the fluctuation, but the particle production is so violent that some finite amount survives to arbitrarily late times. When it has some momentum dependence and it's controlled by the Hubble rate. Okay, so that's the case that we believe is the massless case is the one that we believe is responsible for formation of density perturbations. Okay, so that's the most important, that's the most interesting, most important case. Is the massless, it's the lightest mode you could have. By the way, if you repeat this for spinning fields, the story becomes interesting. For gravitational fields, if you quantize a spin 2 particle, then the massless case is the graviton, and more or less the same story goes through, and you have a frozen amount of perturbations, also of order h. For vectors, it doesn't work. Why? Why don't you produce photons in the de Sitter space? What's special about Maxwell theory compared to GR or the free scalar? No, gravity is gauge invariant. Conformal. It doesn't care that it's in de Sitter space. It's the same as if it's in flat space. So it behaves more like this example here. So it dilutes, it falls off as eta to the 1. Okay, so in fact, that's a big puzzle. Okay, sorry, let's, I know we like theory here, but just a little phenomenological puzzle. There is some evidence, maybe debatable, that there are primordial magnetic fields in the universe, meaning there are magnetic fields that are correlated over long enough scales that they probably had to be there at the beginning of the universe, and there is no reasonable mechanism to generate them during inflation for this reason. Because if you try the dumbest thing to write the Maxwell Lagrangian, you don't produce anything. So people try Baroque things and they run into trouble. Yeah. Well, the discussion of yesterday, what was the idea? That if you are in the vacuum, in the past, you should have only positive frequency. And then as you go to the future, if there is no particle production, you should again see only positive frequency, right? Now, because then from the point of view of a Geiger counter in the future, you should only measure positive frequencies if you're in the vacuum state. If you see an admixture, then you'll see clicks in your Geiger counter. And the fact that you control, you just feed in this boundary condition, you solve the equation, and whatever you get, you get. And then you find that here there is some admixture, so there is particle production. Yesterday I was drawing some curve, right, U of t, and now the U of t is just coming from the expansion of the universe. Is that now I erase it as 1 over eta type of potential. So that's what's producing particles now. Okay. All right. So if there are no further questions about this, then I'll give you a crash course on inflation. That's my next thing on the order of the day, and then we'll get closer to Bootstrap. So let me start a new item. Inflation. It's a bit of an interlude, okay? So, well, inflation was really developed, as I told you yesterday, was developed to solve some fine-tuning issues of the universe. Why the universe looks so homogeneous and isotropic. And the way to do it is to just make the universe really come from a smaller region. So you homogenize the universe by saying, wow, it really came from a very small patch in some earlier phase, before the hot Big Bang. Moreover, it explains the causality puzzles of the microwave background. So the microwave background is emitted, the microwave background is emitted when the universe is rather young, 400,000 years old, a bit less. And if you look in the sky, you don't need to look very far. If you look in the sky and you see correlations over small angular scales, like if you look at the past light cone in the hot Big Bang of the CMB, these points had no rights to ever be in causal contact. So how come the temperature is so homogeneous? There is no causality argument. And inflation solves this problem by just giving more time. Okay, whoop, I've messed up, but so these points become into causal contact because earlier on during inflation, they were within the domain of dependence of their past light cones. Okay, and the perturbations come from this type of particle production. So there will be some pair production events here, and it deposits a little bit of energy here that creates a hot spot that is correlated with a hot spot over there in the CMB. So now I told you that, well, there's some scalar field that gives rise to inflation, and its quantum fluctuations will give rise to these density perturbations. But we need to explain a couple of things. First, how it affects curvature, which was a question by someone. You shifted the landscape today. By someone who was over there yesterday. We're going to see there's some sort of Higgs mechanism that you can eat the scalar perturbation into the metric. And we need to explain the hierarchy. Why don't we see gravitational perturbations? We only see scalar perturbations. So we're going to explain the hierarchy. So we need acceleration to have inflation. We have no idea where it comes from. The only thing we really see are the imprints of the perturbations. So we need to work under some model building umbrella, which maybe people take it too seriously. But you should keep that in mind. Okay, models are useful so that you have somewhere to start the discussion. But the fact that there is a model doesn't mean that that's how the universe operates. Right? So maybe if you think that this model of inflation is bogus, you're free to generate another one. The only thing you really need to explain are the properties of the perturbations. So the simplest model, the dumbest thing you could write that explains this period. So you need some effective cosmological constant, but you need this to stop. So instead of writing a cosmological constant in the action, you add a scalar field with a potential. So the potential has a heel, where it effectively, if the scalar sits there, it acts as a cosmological constant. And then the scalar rolls down and inflation stops. That's it. Okay. This is called single field slow roll inflation. So single field slow roll inflation. It's the simplest. It's like the Landau-Ginzburg theories. There's some scalar. It's some order parameter for what's going on during inflation. We have no idea if it's fundamental, if it's even this mechanism, but it's the minimal scenario that achieves the job. But you should not buy all of its predictions as saying this is what nature should do. There's a lot of room for model building around the predictions of this model. So what's the picture? You have some fundamental scalar that people call the inflaton, and the scalar has a potential. And a lot of string cosmology is about building a theory of this potential, okay? But we're going to assume that it's given to us. It needs to be fairly flat. We're going to take it as flat. And then there's, for some reason, I'm sweeping under the rug the basic criticisms of inflation. You need to buy that the scalar field starts life somewhere up the hill here. Why not down here? I don't know. But if you accept that it starts here, life, then it will roll down dynamically. And you have some classical solution in which for a long time, the dynamics of there, it will back react on the space-time through Einstein's equations. So this will effectively engineer cosmological constants, and the universe will be well approximated by de Sitter space. At some point, this is a bad approximation. The scalar field rolls down. There is a point in which, let's say, phi end, some value of phi at which inflation stops. There's some technical way of deciding when inflation stops. And then the idea is that if it rolls to the bottom of a potential, then you start the hot Big Bang, because the scalar will oscillate. You couple it to the standard model, it will dump its energy into this oscillatory energy, it will dump its energy into the standard model and thermalize and get into the hot Big Bang. This is very hard. It's a bit of a fairy tale. It's hard to test in practice. It's called reheating. It's very beautiful, the theory of how the oscillations of the scalar field dump their energy into the standard model and thermalize the universe. But because there's thermalization, it erases the past. So it's hard to test whether this really happened. Okay. So for example, people think, oh, maybe you form some crazy topological defect that survives, that doesn't get washed out by thermal perturbation, so we can look for this. But first of all, this happens towards the end of inflation at very short scales, so that the de Sitter stretching of space-time stops. So it happens at short scales, and moreover, the universe is thermalized. Here, the fluctuations are stretched. They are imprinted over super large scales. So even if all hell is breaking loose at short distances, it doesn't affect, more or less by causality, the correlations at long distances. That's why inflation is predictive. Okay, so now this is the classical picture. And you should really think of inflation, if you eat the perturbations of this scalar field into a redefinition of the metric, you should think of this inflation as the theory of a clock. Okay. So the scalar field can quantum mechanically fluctuate in different regions. Don't worry, there are equations, okay? But I'm just trying to draw some pictures to get you some intuition. So there is some classic history of the scalar field. Phi 1, Phi 2, Phi 3. At some point, you reach Phi end. Okay? Phi end. And now, let's say that each point in space tracks the same history, classically. But then quantum mechanically, let's say this point here, let's say the one that gets a kick in this direction, let me call 1. Then 2 is the one that gets kicked forward, and 3 is the one that more or less follows the classical trajectory. So let's benchmark. Let me see if I don't mess this up. So 1 gets kicked further, so it delays the going down. That means that inflation lasts longer for the 1 timeline, because you stop when you reach here. You're trying to go down the hill. Space-time is inflating around you, but you get a little kick. So your history gets delayed. You inflate more. Okay? So this is 1. So you end up with a bigger space-time. So your history lasts longer till the end of inflation. Now, let's say that 3 is some benchmark, and 2, instead, you get kicked down the slope, so inflation stops earlier. Okay. So if you start 1, 2, and 3 more or less at the same time slice, let's say you set this to have 0 curvature, towards the end of inflation, this surface here gets bumpy, and you get some intrinsic curvature. That's what's going on. Okay? So inflation is the theory of a clock. It's even among the specialists, people sometimes call single clock inflation. There's one clock that runs the game. Okay. I hope that's intuitive. So perturbations are the meat, okay? We really don't observe this stuff, the classical motion, let's say the whole potential and this whole space-time. What we really observe is the mismatch, okay? What we really observe are these differences because they affect clustering of stuff in the universe, temperature perturbations, galaxy perturbations. So that's the meat of inflation. That's why cosmologists care. It's not because of a potential, gut scale, and so on. Great, it's beautiful, but people care because it's a theory of structure formation of the universe. Okay, you can go and test. So we should keep that in mind. Soon we'll be in completely theoretical land, no connection to experiments, but we should keep that in mind. Observing the actual background evolution is tricky, and maybe in a couple of lectures I'll comment on how you could imagine doing that. You need some tracer, some particle that really, if I look at correlation functions, I move points around, I have some tracer that really slices this geometry in different ways. But right now we don't have the tool to observe this. There's a fun Higgs mechanism going on here, so I should comment on that. Famously, there's no Higgs mechanism for gravity. You can try. There is some actual obstruction because spin 2 is not the same as spin 1. But the no-go is for relativistic field theory. That is to say, starting from a graviton of 2 degrees of freedom, spin 2 massless, there's no way of engineering some vector scalar Higgsing stuff that you end up eating these 3 extra degrees of freedom and ending up with a heavy graviton with 5 degrees of freedom. That doesn't exist. You can even, there's some nice amplitudes argument that you can show it's not possible. For gauge bosons, of course, you can. But if you break Lorentz symmetry, then you can do something amusing, which is you can decide to use this as a clock to slice the universe of the T1, T2, T3. That's to say, you had a scalar field phi that depended on T of X that you should describe as a classical history plus some perturbation, delta phi. That's what we were describing there with the arrows. But you can go to a gauge, to some unitary gauge in which this is 0. But if you do that, where's the perturbation? It gets eaten in the metric. So the metric, Gij, will have now a graviton and a scalar degree of freedom. And that's the zeta I was mentioning in the first lecture. Okay, so zeta is a scalar modulation. It's a longitudinal modulation of the metric at each point. It's just the Higgs mechanism, you ate this scalar perturbation. But notice there's no clash with representation theory because you're not, well, inflation even breaks de Sitter symmetry. So it carries 3 degrees of freedom. It's completely acceptable. There's not violating any no-go. So the local, by the way, this zeta is, the Laplacian of zeta is the local curvature, is the local Ricci scalar, okay? So if you want to take a little patch of the universe at the end of inflation and you know zeta, you compare zetas around, you compute the Laplacian, and you know the local bumpiness of the universe. Okay. Questions? Gamma ij is the gravitational waves, right? So right. So let's do. Yeah, maybe I need to write. Let me write the action of a single field. So the simplest action that you can write of single fields low rho inflation is the following. So it's 1/2 into So just GR and a scalar field with a potential, that potential up there. Okay. So how many degrees of freedom does this theory have? How many degrees of freedom? 1, 2, 3, 4, 5, infinity. 3, right answer. So 2 gravitational degrees of freedom and 1 scalar. Okay. So well, but let's. You remember how the counting works for GR? Maybe Andrea reviewed. So you have G mu nu. It has 10 degrees of freedom, right? So let's say it's the equation 2 equals 10 minus 4 minus 4, right? So the metric has 10 entries. You have 4 gauge symmetries, but 4 components of the metric are constrained. They don't have dynamics. They are Lagrange multipliers. So you get 2 physical degrees of freedom. Okay? Just like for gauge theory is like 2 equals 4 minus 1 minus 1, right? You have 1 gauge symmetry and the Gauss law. Gauss's law is the minus 1, the extra constraint. Here you have 4 constraints coming from the fact that well, the energy and the momenta that you put in the system are constrained. So you get 2 from this plus the scalar, So that's where the 3 degrees of freedom come from. So your question was about what's gamma ij, right? So gamma ij are these 2 degrees of freedom, and this is the scalar degree of freedom, okay? So that's to say that you can describe the perturbations in this system, maybe. So this, when you want to describe inflation, you need a classical, there's a background solution. There will be a background solution of the equations of motion. It's going to be characterized by some scale factor, A of t, and some scalar field profile, phi of t. Okay? Now there are the perturbations of this solution. And then there are 2 gauge choices. So there are 3 of them, and but there are 2 gauge choices. Gauge choice number 1 is to think about tensor modes inside of the metric. Just get to 2 from 10 minus 4 minus 4, plus delta phi, scalar field perturbations. Choice number 2 is to set delta phi to 0, and then slice space-time. It's going to be a slightly different graviton, and it's like the Higgs mechanism. It's literally like the Higgs mechanism. You go to unitary gauge, you remove the perturbations of the scalar field, and they get eaten by the gauge boson. So you can do that because there is a classical background solution. Okay, so it takes some work to quantize this theory. Even if you want to describe it at quadratic level, it's not so trivial to do it in real time. But what will happen is that these guys, these 3 degrees of freedom, they are essentially massless. Okay, there will be essentially 3 massless fields, but their action has different coefficients up front. So when you compute, remember I told you that the 2-point function is controlled by the Hubble scale, because the classical solution goes like h, but I canonically quantized. I put a 1 in front of the action. So if you canonically quantize, then the perturbations are always order h, but now if there's a number in front of the action, the 2-point function will depend on the value of this number, right? You just do the field redefinition and you see. That's what generates the hierarchy between the 2-point function of this guy and this guy, because they're equipped to different scales. The gravity waves, they care about the Planck scale. And the scalar perturbations, they care about scale that is intrinsic to the potential. So that's how you generate the hierarchy between scalar fluctuations are much bigger than gravitational perturbations, okay? Does that make sense? It's important, otherwise inflation is ruled out. We would have seen gravitational waves in the sky and we don't see them, right? We know they're much weaker than scalar perturbations by at least 2 orders of magnitude. So to generate this hierarchy, we generate it because there are 2 scales in the problem. There's some intrinsic energy scale associated to the scalar, to the properties of the potential, how slowly you're rolling, what's the scale at which the scalar perturbations become strongly coupled, if you wish. There's some intrinsic strong coupling scale for the scalars, which is, if you wish, a free parameter. For sure, it cannot be at the Planck scale. Otherwise, what are we talking about? And then the gravitational waves, they care about the ratio between the Hubble scale and the Planck scale. Okay. So that's how you generate the hierarchy. Let me put some meat into these words. So let me describe the background solution. So the metric is given by this. So the Einstein plus Klein-Gordon equations give you, well, there are 3 equations, of course, 2 Einstein equations. If you wish, 0, 0, and I, Einstein equations, and the Klein-Gordon equations, but there are really 2 equations. The third one is automatic. So they look like this. This is for the background, okay? And they make a whole lot of sense. By the way, M Planck is defined as 1 over 8 pi g Newton. I like, there's a cute footnotes in the paper of Maldacena about this. It says, we use a different definition of the Planck mass that different than the one that Planck used. So it's just to make the kinetic term looks like R over 2. That's not usually how you define the Planck scale. But now it's standard in the inflationary literature. So what are these equations? This is just the total energy, kinetic plus potential energy, gives you the Hubble rates of the universe, okay? So H is defined the usual way. Now we're not doing de Sitter. It's true inflation. The space-time has some dynamics that is time dependent. So Hubble is defined as A dot over A, okay? The logarithmic derivative of A. So it has time dependence, okay? De Sitter space, this would be 0. So you would need 0 kinetic term. So as the scalar field rolls down the hill, it diminishes the Hubble scale. That's it. Okay, that's the picture of the scalar rolling down the hill and lowering the Hubble rates. If the scalar field rolls down very slowly, then this Hubble rate change is very small. Everything measured in Hubble units. And then you should neglect in the energy budget, the scalar, the potential energy should be very small compared to the kinetic energy should be much smaller than the potential energy. This is called slow roll. When we say single field slow roll inflation, it literally means the scalar field rolls very slowly, so it has very small kinetic energy and the potential energy is large. So you're supposed to at first neglect this. The potential gives you the Hubble rate, and once you put back in the kinetic energy, it gives you a very small time variation of the Hubble rate. That's the background solution. So assuming that, so slow roll V of phi in the classical solution is much bigger than phi bar, V of phi bar dot squared over 2. Okay? There is a more technical way of defining this. So I said it many times, so now let me just do it. something called slow roll parameters. Why is what? Best question. It's answered by itself. Okay. Everything okay? Any other questions or? So slow roll parameters. These are just dimensionless parameters that tell you how close you are to pure de Sitter. This is just some dimensionless thing that you build out of the Hubble scale that controls how slowly the Hubble scale is changing with time. And we define, end of inflation ends. So in the de Sitter space, this is 0. So there's like as good inflation as you can get. And we are happy to have inflation as long as epsilon is less than 1. Okay, so epsilon equals 1 end of inflation. So that's how we technically define inflation to be over. But the slow roll approximation, we're going to take epsilon to be very small, but non-zero. Okay, so slow roll approximation is epsilon much less than 1, but non-zero. That's what we're going to use. We don't see, anyway, that's enough. Then you also need the, if you wish, the effective mass term or the rate of change of this parameter to be small in the usual slow roll inflation. So again, you build something, the logarithmic derivative of this epsilon needs to be small. It's related to the first and second derivative of the potential of V of phi. You can trade using the Friedman equation. You can trade V prime and V double prime for these two parameters. Bad notation, this eta has nothing to do with conformal time. It's just some proxy for how slowly you're rolling. But it's standard notation, okay? Sorry. It is called the eta parameter. It's really related to the second derivative of V. It's related to the effective mass of the potential. So you want epsilon and eta to be much smaller than 1. Eta doesn't need to be much smaller than 1. It's useful for calculational purposes. Meaning there are models of inflation for which epsilon always needs to be relatively small, but eta can be even big sometimes. Spectacular things can happen. So, but we're going to do the vanilla thing. So the fluctuations, so the perturbations. I'm going to describe the gauge in which all the perturbations are in the metric. So we foliate space-time, with phi of t of x equals phi bar of t. So there's no scalar perturbation. So the scalar perturbation appears in the metric, a la Higgs. So the metric is G mu nu. The zero components of the metric are constrained. So they really are not dynamical. They depend on the dynamical fields indirectly. And Gij, now you have six entries in this 3x3 matrix. And it will carry the physical degrees of freedom. And you can choose your gauge you can choose your gauge to well, you only have 3 more. You already used 1 out of the 4 gauge freedoms. You pick the clock by deciding that the scalar field foliates space-time. So now you have the 3 choices of frame, spatial frame, and you're going to go from 6 to 3 degrees of freedom. And then there will be a scalar mode. So it contains the physical degrees of freedom, which will be the graviton, and this scalar perturbation. So you write something like this. The spatial metric is given by, so the background solution, of course, there will be a squared of t. There will be some breathing mode, some local modulation of the scale factor, plus some shear. And this is traceless transverse. So we'll have 2 degrees of freedom, okay? So these are the tensor modes, the gravitational waves, and these are the scalar perturbations, okay? So this is the Higgsing. So now it appeared as a component of the metric. So how are you supposed to do this? And this I'm sweeping things under the rug because it takes work to do it properly. You take this action, you write, I need to tell you how to write the full metric of the space-time. There's a nice way of doing that. It's called ADM. ADM formalism, Arno Wideser Meissner. They taught us how to write the metric in 3+1 decomposition, so that you specify the spatial metric and you can cleanly identify the other 4 parts of the metric, how to rewrite the G0 mu so that they're automatically Lagrange multipliers, okay? So there will be 4 Lagrange multipliers, the G0 mu, G00, G01, G02, G03. They will give you constraints. You're supposed to solve these constraints. There will be functions of this zeta and gamma ij. You plug it back in the metric. It's like doing electrodynamics in Coulomb gauge, if you remember 100 years ago when you took QFT1, right? So when you do electrodynamics in Coulomb gauge, funny things happen. The Lorentz symmetry is not manifest. You get inverse Laplacians. Same stuff will happen here. The nice thing about Coulomb gauge is that you talk about the physical degree of freedom straight up. Okay, you lose covariance and Lorentz symmetry, but at least you gain the fact that everything is physical and clean. So here we're talking about the physical degrees of freedom, zeta and gamma ij, but the action will be relatively complicated. At quadratic level, it's not so bad. It turns out, well, at quadratic level, the only thing you can write is a kinetic term and a mass term, right? And because of rotational symmetry, there's no mixing between, there's no cross term. There's no linear mixing zeta gamma. So you're going to have a quadratic action for zeta, a quadratic action for gamma. And when the dust settles, the result is very simple. Here. When the dust settles, this is what you get. Remember that in this low row approximation, the background metric is almost like the Sitter space. You keep track of just slow row parameters as small parameters, and this is what you get. So you get a quadratic action for the scalar perturbation and a quadratic action for the gravitational perturbation. So this is quadratic. The moment you go beyond quadratic, then this beautiful story becomes complicated. But this is the answer. G background, epsilon, G bar mu nu, D bar mu zeta. That's it. It takes some work to get this, but it's nice to see the final result. So it looks like you can think of G bar as the de Sitter metric, because for inflation, the moment you kept track of leading slow row approximations, then you can just plug in the de Sitter metric. So these are just these gamma. The indices are summed with the Euclidean metric. So for all practical purposes, you got 3 free massless scalar fields in the Sitter space. The difference is here. This guy has an F, and this guy doesn't. So this one, this epsilon is very small, when you canonically normalize, it will appear downstairs in the two-point function, so it boosts the two-point function. Well, this guy is Planck suppressed. Okay, that's the difference. It looks Planck suppressed, but it's a bit of a hoax. If you go back to the Friedman equation, you see if you divide by h squared on both sides, it's really sensitive to phi dot. That's the scale. So with the scale, if the scalar perturbations become as big as the speed of the scalar, then you went into strong coupling, right? Because you're tracking some classical motion, and you're saying my perturbations are as big as the velocity with which I'm moving. So m Planck squared epsilon is really phi bar dot squared. So if the scalar perturbations become of the order of the speed of the scalar, they become strongly coupled. While the gravitational perturbations become strongly coupled at the Planck scale, which is what everyone expects. Okay. So even though it looks like they're both Planck suppressed, this epsilon is doing the heavy work here. And the hard work is to get the epsilon. Now it looks very simple, but I invite you to try at home. It is kind of a tour de force to get it. Not so bad also. I can do it maybe after steak, no, but so what do you get? So then you quantize like you would. So in the beginning of the lecture, like parentheses, remember we quantized, we took the scalar as phi. Well, now let's do the massless scalar, which was root g bar 1/2 minus d mu phi squared. Okay? We said that phi k classical is h over root 2k cubed, 1 plus ik eta, e to the minus ik eta. Now if you compute the two-point function, phi, what is it? You stick in the harmonic, the field operator, has a creation and annihilation operator. At quadratic level is just the classical solution, right? It's just the mod squared, phi k classical mod squared. And that will be because of translation invariance. If I do k and k prime, k plus k prime, right? Just from doing the Fourier transform over the spatial part. Okay, that's not surprising. That's the, does that make clear? You take the field operator, depends on space and time. You Fourier transform, write the Fourier expansion of the mode at point x and point y. Now you Fourier transform, you pick certain harmonic oscillators. You're only going to get a non-zero product if the k's add up to 0. You get a delta function. Okay, this is just translation invariance. The fact that the two-point function depends on x minus y. And you get the classical solution, so the mod squared. So if you look at this here, it's, well, the phase drops out and you get, by the way, I'm mostly going to ignore this delta function because otherwise we spend half of the rest of the lectures writing delta functions, okay? So always keep in mind there's only one mode, only one scale, phi k, so there's going to be phi k, phi minus k is going to be h squared over 2k cubed, 1 plus k eta squared. Okay? So at what eta should you evaluate this? So as long as the mode crossed the horizon, when eta is k eta is much less than 1, you see you make a very small mistake by just neglecting this compared to 1. Okay? So you can just drop it. So we usually say that inflation lasts long enough that the modes that we observe, they are outside of the horizon for a while, so we're going to essentially send eta to 0. Okay? That's a good approximation. Most of the fun comes from k eta order 1, and after that you make exponentially small mistake by neglecting the further time evolution once the mode is outside of the horizon. Okay? So in practice we send eta to 0, but keep in mind the best approximation is k eta order 1, okay, for each mode. So for each k, you're going to evaluate this at a given eta. Why am I saying that? Because in inflation, h is not constant. So each mode will cross the horizon and feel a slightly different h, right? Because h is time dependent. Every time a mode crosses through the horizon, experiences a slightly different value of h. So h is secretly a function of k. So you should keep that in mind. So if you actually do this for inflation rather than de Sitter physics, then you should remember that h has a very small k dependence, okay? And we're gonna use that in a second. So that's it. So this comes from quantization of a massless scalar in de Sitter space. You get a 2-point function that goes like h squared over k cubed. And this scaling invariant, by the way. Just take just by dimensional analysis, right? If you take a 2-point function that doesn't depend on scale, it should not have x, y dependence. If you do the Fourier transform by dimensional analysis, it should go like 1 over k cubes, right? You need to put some log to make sense of the. It's almost scaling invariant, but if you make it be a power law, you see that in the limit that it becomes scaling invariant, the 2-point function will go like 1 over k cubed. So that's exact scaling invariance. Now let's go back to inflation. It looks exactly like a massless scalar, but now to canonically normalize, we should. So the canonical, let's say, zeta canonical is what? Zeta. Sorry. Yes, zeta divided by m Planck root epsilon, right? While gamma canonical is gamma divided by m Planck. Maybe with okay, some factor. I don't care about the factor of 2. Okay, it's 2 or whatever. Maybe there's a root 2 here. So that means that the 2-point function of zeta then will have h squared. Sorry, I don't. Sorry, guys, I'm just being stupid. So now, yes, if I called this object zeta canonical, the action is just d zeta canonical squared, and okay. Now, then it means that zeta canonical 2-point function is h squared. Therefore, the zeta 2-point function is going to be h squared over m Planck squared epsilon k cubed. And the gamma 2-point function is going to be h squared over maybe 2 here. 4. 8. 4. 8. I'm sure that the factors of 2 are completely wrong, okay? But the important thing is the scaling. So because epsilon is very small, you boost. So remember, this is really h over phi bar dot squared, the strong coupling scale for the scalar, while this is h over m Planck squared, the strongly coupled scale for the graviton. So why do we care so much about measuring gravitational waves? Because if you measure them, you know the Hubble scaling Planck units. And 10 years ago, when you were 10 years ago, where were you? Like high school, grade school? Maybe don't tell me. So 10 years ago, there was a claim detection of primordial gravitational waves. And this implied that this number is relatively small, that h is ordered 10 to the 14 GeV, meaning we're 5 orders of magnitude away from the Planck scale during inflation. That would be fantastic, no? Can you imagine? Nature just hands to you in a plate the theory of the initial conditions is coming at an energy scale, energy density scale that is 5 orders of magnitude away from the Planck scale. And you care about string theory, that's why you're here. The string scale cannot be sitting on top of the Planck scale, it needs to be lower. By the way, 10 to the 14 GeV is the gut scale, and there's no apparent connection. So the scale of inflation happens to be, for dumb models of inflation, very close to the gut scale. So is this a coincidence? Is it not? Anyway, so if you measure gravitational waves in the foreseeable future, we're not very far from gut scale physics. Okay, gut scale physics. So that would be pretty sweet. So right now, the only thing we know is this ratio. So because of the 10 to the minus 5, we know that phi bar dot is order 100 or 60 h. Okay, but we can't tell. We need a second measurement to really be able to pin h, because this we know. Right? So this is kind of a free parameter. It's not easy to model build around this. So if you detect gravitational waves, it's more or less clean, always with caveats, but more or less clean that you're detecting the Hubble scale in Planck units. So that would be pretty sweet. Right now, we just have a bound on the ratio of the 2-point function of gravitons to the 2-point function of scalars. We call it the tensor to scalar ratio. That's denoted by R. And actually, it's still more or less driven by the experiment that claimed the detection. It's less than 10 to the minus 2. Give or take the 5 times 10 to the minus 2. So gravitational perturbations are weaker than scalar perturbations by at least an order of magnitude, maybe more. And in the next decade, if you have a theory, if you can tell me string theory predicts we're around the corner, wonderful. Or you can say we're never going to see anything. The tensor to scalar ratio in string theory must be 10 to the minus 10. Maybe it's a prediction, I don't know, it's a negative result, but for sure we're going to improve on this bound in the next decade by at least an order of magnitude. Okay, so next decade, hopefully we see something, but expect R less than 10 to the minus 3. Okay, or detection. If you see anything, H go is if you see something, H would be order 10 to the 13 GeV. This is amazing, huh? 10 to the 13 GeV handed to you. I stop at 6, is that true or? Huh? 5:45. I have 15 minutes. Okay. So one thing is that how do we remember from yesterday that the scalar, here they look scale invariant. I was plotting yesterday k cubed zeta zeta as a function of scale, and I said they have some scale dependence. It's really coming from k dependence here. Okay, so these guys have scale dependence, and so does this guy here. So remember that each mode, as it crosses the, so this, to say that you're quantizing fields in de Sitter space is approximate, and you make a good estimate if you evaluate the Hubble parameters at horizon crossing, okay? So that means that this should always be evaluated at time order 1 over k. So because these are k dependent, you can use, it's a kind of a fun exercise to work it out. You'll see that there's some scale dependence that is controlled by those low row parameters. So you will find that actually this goes like k to the ns minus 1 and ns minus 1. Remember that this is a historical accident. It's just the exponent. and S minus 1 in slow roll inflation is minus 2 epsilon minus eta. And this has been measured. Okay, so now let me tell you a story that makes you, if you have $1 billion in your pockets and you want to invest on a gravitational wave detector, let me tell you a story that will make you convinced. So R is order epsilon. You just take the ratio here and you see that it's order epsilon, right? Gamma gamma divided by zeta zeta, you get epsilon. It's like 10 epsilon. We haven't seen this, but this we have seen. It's order 10 to the minus 2. It's the number I quoted to you yesterday. Okay. So now epsilon and eta maybe are comparable to each other. Therefore, if this is order 10 to the minus 2, epsilon is order 10 to the minus 2, the tensor to scalar ratio should be order 10 to the minus 2. So we're around the corner. That's it. Okay? Of course, you can fine tune and say, no, it's all driven by eta. Epsilon is 10 to the minus 100. It could be. But if you use some naturalness umbrella that all parameters are more or less the same, unless there's some big symmetry that separates them, then maybe we are around the corner. If you buy this whole framework of single field slow roll inflation, we are around the corner. And if we're gonna, just the option is to make you happy at night when you, oh my God. And then we're around the corner and we're gonna see physics at 10 to the 13 GeV. You can model build your way around this. String theory will predict that R is 10 to the minus 10, in which case there is no known probe in the universe that will be able to reach such low level of the tensor to scalar ratio. Because you see, to detect gravitation, so scalar waves, they produce a big potential well and stuff clusters, so it's easy. Structure grows around them, so they leave big spikes in the matter distribution of the universe. Gravitational waves, they generate tidal fields, so they don't make stuff cluster, they just like shears stuff. So their amplitude doesn't grow when they start time evolving in FRW cosmology. So they generate shear. So the way you look for them in the CMB is, let me pull back. The way you look for them in the CMB is you look at the polarization of the photons, and there will be swirling like patterns in the polarization. They are characteristic of gravitational waves. The scalar waves cannot induce. Imagine that the polarizations, they just make little like, what's the word in English? Little tornadoes, okay? So if the polarization they create fish like a little vortices, yeah, exactly. They create some sort of vorticity in the polarization field. If you measure that, then it's intrinsic to gravitational waves, okay? And it just so happens that because of dirty physics of the CMB, unless you see it at this level, you're never going to see it from the CMB. In galaxies, it does leave an imprint, but right now, I think it's science fiction. The idea is that it creates intrinsic alignments between galaxies. So if you see a cluster of galaxies over here, a cluster of galaxies over there, if there is a big gravitational wave that modulated these clusters, you would see that the galaxies tend to be all aligned in this direction, correlated with another direction over there. This is very hard to detect in practice. That's one proposal. Okay. So that's all we know about inflation, really. That's all we know. And even putting it under the umbrella of single field slow roll is already assuming stuff. So let's go further. And tomorrow, we're going to talk about item 6, primordial non-Gaussianity. Scary name, right? Scary name. When I first heard, what the heck is this, some technicality? What is it, primordial non-Gaussianity? It's interactions. So this is just free field theory, right? You just described the quadratic Lagrangian of the density and gravitational perturbations. If they interact, then you have an interesting 3-point function, you have Feynman diagrams, you have a 4-point function. Therefore, the density field is not a Gaussian distribution. You can't just use Wick's theorem to compute the 4-point function, 6-point function, and so on. And because it's not Gaussian, it's called non-Gaussianity, okay? And the universe is highly non-Gaussian, of course, because we are here. There's like a 60-point correlation function that is very big right now, right, at a given geometry. But that's because of late universe evolution. You're interested in the density field at the hot Big Bang has non-Gaussian statistics. So remember, at the end of inflation, we just described the diagram of a free field theory. Okay, it happens at all scales, so we get an interesting 2-point function. At all scales, each scale experiences slightly different Hubble rates, but we just described pair production, free field theory. What about going beyond? What if I look at now 3 points? What kind of physics story should I tell for what's going on? What gives rise to this 3-point function? So this is what primordial non-Gaussianity is all about. So there are a few some obvious possibilities. Right? So what could this be? It can be self-interactions, right? The most boring possibility. The scalar field just self-interact. It can be an interaction mediated by a new field. Maybe there's a mediator, something that we can't observe directly. Here. There's a messenger. Maybe the messenger is massive. The messenger of order Hubble. It redshifts too fast. Redshifts like matter. So we can't observe it. Remember that to observe something at the end of inflation, it needs to be almost massless. Otherwise, it redshifts away all of its power. But it doesn't redshift away instantaneously. Maybe it can travel a few Hubble volumes and then decay into massless stuff. In which case, you imprint some non-local interaction. Because as it travels, it couples stuff that was formed earlier during inflation to stuff that was formed later during inflation. So you see that this will be the theme for the rest of the lectures. There is some fun interplay between time and space here. So if you probe different spatial configurations, things that are nearby, they have to be sourced towards the end of inflation because they didn't inflate too much. Now, if you probe long-distance correlations, you're probing long time scales because they need to be formed earlier in inflation. So you're seeing time evolution without having access to a timeline. So these are self-interactions. These are interactions with a mediator. So now you can ask questions about the spectroscopy of the mediator. How does it depend on the mass of the mediator, the spin of the mediator, and so on. It can be a tree-level. This is a tree-level diagram. It can be a loop. It can be that you have some strongly coupled sector. There's some QCD-like thing that has some interesting 2-point function that couples these modes. And you can ask the same question for the graviton, okay? You can also ask similar question for graviton. Maybe graviton can now correlate with a scalar even. Oops. So So you can now look at the mixed correlators of graviton with scalar and so on and so forth. I'm done. Is that true? And you're probably completely done also. So, okay. I will not say I have one more thing to say. So tomorrow I'll say. Okay, so I'll continue tomorrow.